All right, so this is January 22, and this is housekeeping stuff that we went over. These are the textbooks. All right, so we talked about vectors last week. So let me see, what time is it now? Okay, 9:57. So I don't know if you remember, but vector had some properties, right? One, I already listed it. One is the magnitude. What was the other one? Direction, right. Okay, cool. So yeah, so here this diagram is kind of explaining the important terms when representing force as a vector. So yeah, of course, so vector has magnitude, which is typically shown as length of this arrow. So if the arrow is longer, in this case, it's a force, so magnitude of the force is bigger. And if the arrow is shorter, then magnitude of the force is smaller. So yeah, so what's important is the vector is drawn to scale, right? Drawing the magnitude of this vector accurately is the essence of the method of graphic statics. This diagram is from this book, Graphic Statics by Wolf, and that's basically what we are going to be doing with a lot of the calculations in this class. What is a graphic statics? I should probably do a history of graphic statics at some point, but I'm pretty sure you guys did trigonometry, probably, right? It was required or something. And probably you've done vector math before. When you, for example, you probably, to add this and this, you're gonna get the angles between the two arrows, and then you get the cosine and sine, and you do a lot of calculations, and finally get the lengths, which is kind of cumbersome. But the beauty of the vector math is if you draw them completely accurately, you can just measure off of them, right? You can just draw them graphically correct, and you can measure it. And that's what we're going to do because we have access to CAD software. So all kind of in effort of facilitating the conceptual understanding without getting bogged down by a cumbersome calculation. Anyway, Cynthia, so you're here, so that's good. But I'll talk to you later about we're doing the attendance differently this semester. Anyway, so another one was direction, or in this case, there are two terms, direction and sense, which are very kind of two similar concepts. Anyway, direction is basically this, right? Like the rotation angle, you can represent it by sort of an angle against a horizontal line or vertical line or whatever you choose. But let's say your direction is this way. Direction actually does not have a arrow, let's say arrow tip. So direction could be, if I were to graphically represent direction, it could be a sort of a straight arrow with two arrowhead on start point and end point, because direction basically means this way. It doesn't necessarily mean only this way or that way. It could be either this way or that way along this line, right? And sense is basically which way on this direction it is, right? So sense kind of forces you to choose a one arrowhead against another. Does that make sense? Right? So if I read this, I mean, you can read it later, but sometimes the term direction is used to indicate both sense and direction, so it's slightly interchangeable, but strictly speaking, these are two different things. Two other properties. So when you're talking about a force has a line of action, which you can think of it as a sort of this infinite extension on, along the direction of this vector. So basically, a force can be seen as a segment of this infinitely long line, and each force is associated as a characteristic line, which is referred to as its line of action. Anyway, so I'll explain to you more after the next slide, but basically force is acting along this line of action, and you can, wherever you apply that force, as long as it's on this line of action, the effect of that force on its, we call it a body, is the same. So in other words, if I push this bottle up at the bottom, or if I grab it in the middle and up, as long as it's the same direction and magnitude of the force, the effect is the same, right? So because the line of action is kind of this, same thing as if I had a rope hanging from the neck and lift it up, that's still the same effect. So as long as it's along the same line of action, the effect is always the same. Then we're talking about, I want to change the color scheme, I do not. Damn it. So the last thing is point of application. So where the force is applied to a body or an object matters, right? So it's a different story. I mean, I think I described it last week. It's a different story if I push the desk here or here. So where the force is being applied to a body is called point of application, right? So those are the 4 different properties of a vector as a force. So just kind of to supplement the explanation of line of action, as long as it's along this line of action, the force can, as long as it's on the same line of action and same direction and same magnitude, you can move the point of application along this line, and it's going to be basically the same thing, and that's called principle of transmissibility or something. Anyway, that's from this book. Yeah, so that's point of application and that's line of action. So far it's clear? Yeah? Okay, cool. So, vector addition, right? So how do you add vectors, which you probably done in some classes, I guess, right? So so yeah, 2 vectors which have the same magnitude and the same direction can be anywhere and they're equal vectors. Okay, so I'll skip. The negative vector, what does that mean? That simply means the same magnitude but opposite sense. And of course, if you add p and negative p, it's going to be 0. All right, so if you try to add 2 different vectors working at acting at the same point of application. I think I talked about it last week, but these are called concurrent forces because the line of action of the forces intersect. But there are
tap the cat.
Yeah, gotta be careful. I mean, it's just kind of technicality. I mean, like for me, it's pretty much the same. I mean, I find the tip to tail method easier, but there are apparently 2 methods to add 2 vectors. One way is you look at the P and Q, and you draw this parallel line to P and parallel line to Q, and complete this parallelogram, and then you connect the start point and the corner of that parallelogram, and that's P plus Q, which is still kind of counterintuitive. So I find this more direct and intuitive, but it's basically doing the same thing. So that's one method, and another method is called tip to tail method, or could be called triangular method. If you want to add P and Q, it doesn't really matter which order. If you want to add P first, you would go from A and you would go along the arrow P, and at the end point of the P, you're going to bring Q over there. So you connect the 2 vector literally from tip to tail, and you basically go from here and here, so that's your endpoint. So that ends up being P plus Q, and that's basically the opposite order. So it's actually Q plus P, but P plus Q and Q plus P is the same thing. So that's pretty much same as if you were adding numbers, behaves pretty much similarly. And this is if you were to add more than two forces. Here are all the different ways, different orders of adding things, but at the end of the day, it's all the same thing. It's like you could add P, Q, S, and that's P plus Q plus S, and this is doing the P plus Q first, and then adding the S later. And this one's P first and Q plus S later. But you know, same thing. Pretty straightforward. And this is just showing the order with which you add these three. Doesn't really matter. P, Q, S or S, Q, P end up being the same thing. Anyway, so that was just kind of graphic operation. But when we are going to calculate the forces, we will also have to know the magnitude of the resulting force of additions of two. So when you add two forces, you end up with this resultant force, and you also need to know the magnitude of that resultant force. So if you were to add in this case, 30-pound force and 40-pound force perpendicular to each other, first thing that's super important is when you draw this, we're going to be drawing this kind of stuff in Rhino. It's absolutely important that, for example, whatever scale you draw at, this 40-pound force must be exactly 4/3 of 30-pound force. Actually, it's simpler if I say that in the other way. It's absolutely important that this 30-pound force, the length of this arrow is 3/4 of that 40-pound force. So it's got to be proportionately correct all the time. Anyway, force scale. So that's what we call force scale. So when calculating the forces using the vector addition, it is important to be aware of these things, right? So we are representing a force. The unit of the force is pound force, but we're drawing these vectors, you know, whether on the piece of paper or in a CAD software, but they have a length, right? So let's say it's in inches. So we have to come up with some sort of a scale to translate the force, the unit pound force, into inches, which is going to be, whatever you do, it's going to be arbitrary, but you probably want to pick a scale that it's easy for you to calculate. Anyway, in this case, as you can see with this dimension string, we're representing a 30-pound force with 3-inch long arrow. So that means our force scale is 1 inch equal 10-pound force, right? So whenever we will do this calculation, we will have to show what this force scale is, and it has to be consistent from beginning to the end, as long as you know, within the same problem. I mean, if you're gonna solve the next problem, you could use a different scale, but as long as it's in one system, you have to use the consistent force scale, right? Yeah, so it's important to be consistent. So therefore, because this arrow is 4 pounds, that's why this can represent 40-pound force. If this is 4.2 inches, it's going to be 42-pound force. So now, this is probably, I mean, it's fairly simple, but it's important because I realized some people misunderstood it last semester. But so we want to add these two forces by doing a vector addition, and yeah, so what will the magnitude of the resultant force be? Will it be 30 plus 40 and 70-pound force? Yes or no? No, right? So that's one thing that you have to remember, that it's not... Only time this is true is when these two vectors are in same line of action and same direction, same sense, right? That case, it could be 70-pound force, but if they're in different lines of actions or they have an angle between each other, you cannot add these two forces, magnitude of these two forces arithmetically and call it a day. So here's where the vector addition comes in. So we're going to use the tip to tail method. In this case, we're going to start here, go 30 to the right, 40 above. And you might remember this Pythagorean triangle. What would be the, anyone want to guess what the magnitude of the resultant force would be?
50.
50, yes, because 3, 4, 5, right? So 3 squared, which is 9, 4 squared, which is 16, 9 plus 16 is 25, root of 25 is 5, right? So anyway, but I mean, we're going to be drawing this in CAD, so even if you didn't know that, you can measure the lengths in the software, and we can just call it a day. Anyway, so this resultant force would be 5 inches, would be represented by 5-inch long arrow. Therefore, it's 50-pound force. So the arithmetic addition of magnitude of two forces will not give you the correct answer for the magnitude of the resultant force. So that's the most important thing. So far, so good? Yeah? Okay, cool. This is going to be pretty quick, so we're probably going to do the Rhino problem together, or I'll at least demonstrate how to do those. Anyway, so resultant, so here's a new concept. So resultant, I've been talking about as if you add two additions, the result of this addition is called resultant force. So in this case, yeah, that's the resultant force, adding this one and this one. But there's also a concept called anti-resultant, so I will try to explain that, because I'm going to be asking you what the resultant is or anti-resultant is in the homework. All right, so let's imagine a scenario where it's like a river or something, and you have this concrete wall with some angle, right? So what forces are acting here, right? I mean, I should have probably had one image without all of these forces drawn in, but it's not hard to imagine. This massive concrete thing's gotta have its weight, so there's gotta be a gravity force working on this concrete from the center of gravity, which is G. And P will be the force from the water that's pressing against this concrete, right? So that's kind of the known forces so far. So if you add P and G, you end up with this resultant force R. So what does that mean, right? So first question is that are these all of the forces that's present here? Probably not, right? Because if this is all the forces that are present, then what's going to happen is this concrete is going to be moving towards diagonally along the line of action of resultant force R, right? And so that's not happening. That means there's got to be a reaction, which is the exact opposite of this R. I'm calling this anti-resultant, which I will reveal to you next, is so basically PG, and there's got to be this force A that's acting at the face of this concrete, pushing against the water. So that's actually all the existing forces, P, G, and A. And if you connect all of that, right, P and G and A, that's going to it's gonna form this closed polygon, which means if you add force P, force G, force A, right, it's coming from this start point, going to here, going to there, and coming back to this original start point. So which means basically addition of vector P plus vector G plus vector A is basically 0, right? Because all the forces, if you add all these forces, the resultant is 0. That's why nothing is moving. If the resultant force is facing somewhere and had some kind of magnitude, this thing's got to be moving along that direction. So this is good. So basically, when you add all these forces that's acting in this system graphically, and if you end up with this closed polygon, meaning start point and end point at the same point, that means all of these forces are in equilibrium. Equilibrium means that if you add all the forces, it's going to basically become 0, and it's either, I mean, in our case, because we're talking about building structure, if all the forces are in equilibrium, that means your structure is not moving, and we're happy, right? If you're talking about like satellite in space or something, it might be in motion from the beginning and then equilibrium, but we're not talking about that, so let's forget about that. And so equilibrium basically for us means it's static, right? It's not moving. Anyway, so anti-resultant, what this anti-resultant is basically a force that is required to keep the force system in equilibrium given the P and G, right? So does that make sense? Cool. So that was pretty quick. So that's kind of the end of this slideshow, and we have still 10:15, right? So we still have about 45 minutes. So if you want to, so we have an assignment, but this sample problems that I posted here is basically the same exact problems as this assignment, except everything is slightly different, right? So it's not going to be the same answer, but what you have to do is going to be the same. So I think I want to, I mean, we can look at it together, or I can explain it to you. So if I can find it. All right, so sample problems. So if you're not worried about the battery, you can open this file, but let me, for the sake of demonstration, turn this to a top view too. Alright, so in this case the problem that we have is we want to add these vectors. Let's look at the top view. So add the vectors f1 and f2 acting on point 1. So let's imagine, you know, there could be like a ball or something, and then you have these two things pulling on this object at this point, right? F1 and f2. And we want to find the resulting force. Magnitude of force F1 is 200 pound force, F2 is 150 pound force. How do we know that? This is 20 inches. This is 15 inches. So therefore, if 20 inches represent 200 pound force, the force scale has got to be 1 inch equal 10 pound force, right? So that's our force scale, which is, you know, that's important. So anyway, what I would be asking you is that measure the length of the resultant vector and determine its magnitude, right? So measure the length, yeah. Round it to the whole number, right? So if it's like 345.33, then I want it to be 345. So what you do is, I mean, this is not due until next week, but if you can download the Rhino file from here, and then you'll be entering, so the Q1 would be that problem, and you're gonna there were some someone pointed out that, yeah, so the only right answer would be if you type in just the number. So if it's like 432 pounds, just type in 432 and no pounds or nothing else, right? So anyway, because this is a different problem, so it's going to be a different number. But anyway, right? So how do we add these two vectors? It's going to be exactly the same. Super easy in Rhino, right? So you take these two, tip to tail method. I'm going to move this here. So basically your start point is here, your end point is here, right? And your resultant vector, I'm going to draw it as a line first, right? You can show the arrowhead by typing arrowhead and click at the end. If you by mistake added an arrowhead where you don't want to, you can type arrowhead again and click again, right? So anyway, because it's starting from here, ending there, that's the resultant vector. I would type in dot. I'm just gonna call it resultant. So this is your resultant vector, and we want to get the lengths. You can either type in length and get the lengths here, or you could use the linear dimension if you want to. 29.64 inches. Because your force scale was 1 inch, let's say, let's always remember to remember your force scale. So our force scale, 1 inch represents 10 pound force. So because this is 29.64 inches, right? If 1 inch equal 10 pound force, then 29.64 inches must be 296.4 pound force. But in the problem, I've asked you to round it to the closest integer, so it would be 296 pound force, and that would be your magnitude.
So we have to round it after we did the scale, not before. So it's not 300.
No. Yeah. Round it to the integer. Yeah. So, yeah. I mean, this is just so that, I mean, again, for your homework, I'm not really scoring every single, I'm not grading every single one of your homework, so it doesn't really matter if you got 5 points or 4 points or 3 points, but you know, it could be frustrating when you know the answer and it doesn't get the right answer. So that's just for technicality. But what's important is knowing the force scale and being able to dictate what the resultant force is. So this is super easy, right? All right, so next one is once you have the I just realized, yeah, so this is supposed to be the practice problem, but if I already showed the answer, it kind of loses the point. So if this finishes early, I would have you work on the homework problem so that we can work on stuff. But anyway, next one, Q2, it's basically add vectors from, I don't have the label, but there are 7 vectors here. All of them has a length, right? So kind of a random length, I would say, like 10.19 to which you don't have to, but I'm asking you to use a, alright, so add vectors f1 through f7 acting on point p1, right? Use the same force scale as Q1, which was 1 inch equal 10 pound force. So this you don't really have to do, but just so you know, because this one is 10.19 inches, it would be 102 pound force, right? And this would be 152 pound force. So on and so forth. You don't actually need to label all of this, but just know that each of these have specific lengths and it does represent specific magnitude of forces. But all we care about is the addition of all of these vectors, right? And they're all concurrent and it's working, being applied at point 1. So we can do is just do a tip to tail method. Again, the order doesn't matter. So I can, if I want to add all of these, let's say this is the first one, that's the second one, that's the third one, this is the fourth one, fifth, sixth, and seventh. So it started, let's call this a start point. It started at this point. Why is it doing that? It started at this point and ended at that point. Therefore, the resultant vector is going to go from the start point to end point, right? So that's our resultant vector. And before I get the magnitude of this thing, I want to demonstrate the order with which you add up all these vectors does not matter. So let's add these in a different way again. So we had this now. We added from, we basically went clockwise. So let me start from this guy and kind of go in a random order, right? So next one would be this. Next one would be this. And no matter how you add it up, it's always going to be from start point to end point. And that would be your resultant. And just to demonstrate that these two are exactly the same, if I copy this on top of each other, they are identical, right? So actually, no matter how you add them up, whatever the order is, it's going to be the exact same direction and magnitude. So if we get the length of this guy, it's 18.97, and since 1 inch represented 10 pounds, it would be 189.7, so we round it to 190, right? So that would be the answer. Any questions so far? Right, so it's pretty straightforward, and some of you might be bored, but it's kind of fundamental thing. So I mean, it would get more complex, so don't worry. All right. So here's a fewer vectors, but the different thing, I'm asking for a, where is that? Right, so I'm asking for add vectors, all of these four, and find the anti-resultant. Right, so anti-resultant is basically, okay, so let me demonstrate afterwards. But anyway, so to get the anti-resultant, we're gonna add all of these just like we're gonna get the resultant, right? Alright, so if I add all of these four, the resultant would be this guy.
How do you label
The arrow?
no, how do you label the
Oh, you type in dot and type the text, and yeah. Alright, so that's the resultant vector, which is super straightforward. Anti-resultant, as we've seen, is, I can actually type in dir and flip the direction. Anti-resultant is literally what it says, right? It's the exact opposite of resultant, right? So it's the same direction, same line of action, same magnitude, different sense, right? So it's flipped 180 degrees. So what this does, as I've said in the slideshow, anti-resultant is what is required to keep the force system in equilibrium. So basically, if I had this as part of this system, which is actually awfully close to this one, then the addition of all these vectors would be 0, right? So if I add all of these vectors, including the anti-resultant, it's going to close the whole thing, and so it's going to make a closed polygon, making the sum of all these vectors into 0, which means this is in equilibrium, meaning that before without that anti-resultant, you imagine this I don't know, piece of stone or something with you have a center point where the rope is tied, and if someone pulling the point one in this way that much, all of these four people are pulling. What's going to happen is if you add all of these four forces, it's equivalent to that one force. So what's going to happen to that object is it's going to start moving that way, right? Because it's not in equilibrium, and the resultant addition of all these forces are that. So it's basically the same effect. Four people pulling this way and that way, and you can see these two guys pulling the P1 is stronger, right? So it's actually not hard to imagine that if four people are pulling this way, it's going to move that way, right? And what anti-resultant does is to keep, so if you introduce that force here, then basically it's gonna, the total of everything is gonna be 0, so that P1 can stay still. So that's what the anti-resultant is. Alright. Last part is actually, so alright, so now this is actually in 3D. So we're gonna look at in 3D, which is gonna be exactly the same as how we do this in 2D. So basically the same thing that I'm asking in this problem is that go to perspective view and notice these are 3 vectors. Add vectors, F1, there are 13 vectors here. So all of these forces are acting, it's, you know, it's like this object in space being pulled in all these different directions, right? yeah, so we can add all of these forces in any order you like and find the anti-resultant. I'm asking for anti-resultant in this case. Yeah, and same scale. So basically what you do is essentially exactly the same. You don't have to do anything differently. Make sure the project is not on. So I can pick this as a first vector. So basically you add everything tip to tail. Make sure everything is snapped to the endpoint, right? So really how you add it up, the order doesn't really matter. The resultant would be going from here to the endpoint. But in the problem, I'm asking for a anti-resultant. So it would actually be, let's just flip this thing. That's the anti-resultant. So because that's anti-resultant, what it's doing is making the addition of everything into 0, right? So that's the addition. Oops. Alright, so that was all the forces that was acting on the P1, and this was the anti-resultant. So basically what happens is if I bring this here, then you can keep, so without this, P1 would be moving in this way, but because you put anti-resultant, then P1 is in equilibrium and not moving in space. And again, to get the magnitude of this force, we would like to measure the length of this vector. We're still using the same force scale, which is 1 inch equal 10 pound, and because this is 17.784 inches, it would be 178 pound force. Any questions? All right, so it's either too short or too long. So now we have 15 minutes left, and it's too short to go to our next material. So I think the point of this thing is that you actually get to practice in class too. So now you've seen how this is done, and there's actually no use in getting the correct answer for this problem set. So what I would recommend you do is go to the homework, right? Download the file, and there's also one other question about Q3. Pick the one that looks closest to the direction of anti-resultant force. Actually, direction and sense, right? Anyway, so why don't you work on this homework problem, and because the way I want to use this class is one is to demonstrate how you solve it, but also I want you to work on the problem during the class so that I can see if you get it or not, right? At this point, the problems are still super simple, but it's gonna get pretty complex pretty soon. So this in-class exercise is pretty important. So even though it's 15 minutes, why don't we work on the problem, and I walk around and ask questions and answer questions and all that. And yeah, so it doesn't have to be one computer per person. So it might be actually better if you're solving it with someone too, right? So
What?